Most machine learning operates as a mechanical sorting system. It processes historical data to satisfy a specific set of constraints, reacting to inputs based entirely on what it has seen before. These systems rely on feature mapping and frequentist models, such as market basket analysis. They treat human decisions as static outputs, predictable data points that can be graphed and repeated. This classification network thrives on orderly data, funneling specific features into a single reliable output node. But in reality, unpredictable human actors and shifting contexts crash into these rigid pathways, making past spreadsheets useless for navigating uncertain futures. Today, engineers are building algorithms that offer thousands of individual features, yet provide almost no genuine choices. Predicting a user's next action based on their history is not the same as helping them move through a complex, multi-agent environment. To improve these systems, we have to distinguish between selection and choosing. Selection is a statistical extraction. It is picking a single item from a list defined by a provider. Choosing is different. As mapped by researchers like Richard Thaler, it is a neuroeconomic process driven by context, emotion, and the need for perceived freedom. This reveals the paradox of choice. Having the power to decide doesn't guarantee the system has presented a target actually worth choosing. Consider a leadership scenario. You might believe that an executive like Ratan Tata is the ideal candidate for a political office. But if he is unavailable or the system prevents his participation, your ability to choose is capped by a systemic constraint. Instead, you settle for the best available option that meets your standard of acceptance. This proxy creates a psychological goal state, allowing you to feel that you have exercised agency even within a limited boundary. Choice computing is the integration of these behavioral attributes into a rigorous mathematical framework. If AI truly serves humans, it must evolve from a system that selects outputs for us into a system that architects choices with us. We can model a decision space as a mathematical topology. In a standard search tree, the algorithm illuminates one statistically optimal path, leaving all other potential outcomes in the dark. These dark areas represent choice boundaries, the limits placed on you by a system provider, like a fixed menu funneling you toward a specific purchase. Choice architecture removes felt constraints, points of friction, like overwhelming details or cluttered interfaces, that cause users to hesitate. Simultaneously, it implements unfelt constraints, invisible adjustments to pacing. Distracting branches fade away, while core nodes expand to appear infinitely accessible. This process is driven by a choice catalyst algorithm. Unlike a traditional recommendation engine, a catalyst does not force a decision. Instead, it alters the digital environment and the speed at which options are revealed. This is not a form of coercion or simple marketing. It is the alignment of an interface with the user's natural instincts. The goal is to guide users to healthy targets by mathematically curating the space, leaving the user's free will completely intact. This theory has concrete applications in retail. We can transform a standard storefront into a dynamic choice gallery. By curating the environment based on temporal context, like changing fabrics based on the day, we expand perceived boundaries without overwhelming users with inventory. This curation is distinct from showing frequently bought together items. It is an active restructuring of the choosing space itself. We can also apply this to a product like an ice cream machine. A static menu of finished products limits a customer to what the provider has already made. A choice computing solution breaks the product down into discrete flavor nodes, essential raw materials, and varied textures. The customer shifts from being a passive selector of a pre-made tub into an active participant in assembly, increasing the behavioral reward of the experience. This also removes the provider's burden of managing massive inventories of finished goods. Replacing static menus with dynamic, component-level environments maximizes both the user's sense of freedom and the system's overall efficiency. When we apply these principles to large-scale infrastructures, we can achieve systemic behavioral alignment across thousands of people. Look at how smart power grids utilize direct benefit transfers. Under old models, utilities tried forcing behavior through penalties, generating resistance and defaults. By introducing immediate bank transfers upon payment, the system created a new incentive. This shifted probability weights across the user base, turning defaulting nodes green. The system did not mandate a specific behavior. It used a catalyst approach to naturally re-weight the probabilities of individual decisions. We see similar results in the legal kiosk model. Traditional law firms waste significant time using human hierarchies to filter incoming cases. A choice computing agent creates a dual-sided matching system. It allows clients to choose the firm and firms to choose the clients simultaneously. The agent evaluates two distinct fitness functions at the same time to clear the market. Systemic choice architecture scales because it relies on aligning collective incentives with individual freedom. The structural difference is clear. Traditional machine learning is a linear pipeline. You take data, apply statistics, and produce a selection. Choice computing is a circular loop that integrates context, a catalyst, and direct user feedback. This shift upgrades standard utility agents into choice-aware agents. These agents are designed to embed emotional, social, and contextual variables into their learning models. Because these systems influence human behavior, they must be governed by an ethical framework focused on healthy outcomes, targets that provide value without long-term harm. The goal is not manipulation or the use of psychological tricks to limit a user's vision. Instead, success is defined by an optimal outcome that occurs as the natural result of a user freely navigating a curated space. The utility of a system is measured by its ability to empower the user to choose. The next phase of this research focuses on what Parag Kulkarni calls conscious choice machines. In this context, consciousness is a technical requirement. For an agent to truly architect a choice with a human, it must recognize its own role in the loop, understanding how its pacing and presentation impact the user's agency. This mirrors our evolutionary advantage. Sapiens survived because our brains prioritized adaptable choice-making in deeply uncertain environments, not from rigid pattern matching. To build better systems, architects must stop creating algorithms that trap users in statistical feedback loops of their own past. We must design systems that actively maximize behavioral freedom. Artificial intelligence is moving away from rigid prediction and towards systemic behavioral design, using the math of human choice to architect a more cooperative world.